Hi, Assalamualaikum. We are from Group 3. I am Nur Alia. My members are Anis Zulaika Roslan, Nur Sabrina, Nur Fatima, Nurul Anis Auni, and Fatin Fatihah. So today, our group will present about metalloborane. So what is metalloborane? Metalloborane is a metal boron cluster compound which have formed due to reaction between boron anion and metal complexes under different reaction conditions. There are many approaches used to prepare the metalloborane. So it can be prepared by the following methods, but we are going to focus on the first four methods. The first one is metathesis of a boron anion. In this reaction, a boron undergoes reaction with presence of metal hydride to form an anion which on further reaction with metal complex will give a metalloborane. The next method is polyheptocoordination with or without cluster rearrangement. A boron in presence of reagent like triethylamine undergoes reaction with metal complexes to form metalloborane. The special part of this reaction is that the metalloborane forms have diameter center located with the metalloboranes through more than one atomic center, as we can see in the reactions. So another two methods will be presented by Anis Zulaika.
Assalamualaikum. So I will proceed this presentation about the synthesis of metalloborane by the third method, which is oxidative insertion of metal to obtain an expanded cluster. So by using this method, borane will react with metal complex to form metalloborane, and the metal center of the metal complex will undergo oxidation since the oxidation number is increasing. So based on the examples from the slide, we have borane that will react with iridium complex and will form a metalloborane complex. And from here we can see that the oxidation number of iridium is increasing from a +1 to +3. The next synthesis method is deprotonation of metalloborane and further metallation. And by using this method, we have metalloborane that will be treated with hydride base, and after its deprotonation, it will react back with another metal complex to give a new metalloborane. So I will pass this presentation to my group member.
Okay, thank you to Fatima Ujang. So I will proceed the presentation with the bonding in metalloborane. So as you can see, there are many types of bonding in metalloborane, which are mono, di, tri, tetra, penta, and also octa. So these are the ligand that bind to the metal. So there are many metal bind with the borane. Okay, I will explain more about the monoheptoligand. So, monoheptoligand is the classic 2-electron donor acceptor bond is exemplified by the monoheptoligand, which is this one, which donates a pair of electrons into the tetrahedral iron atom as shown in figure below. As you can see in this figure, this is the monoheptoligand that bind to the iron atom. Okay, so for this is about dihepto, which forming a 3-center 2-electron BFEB bond as indicated schematically in figure below. As you can see, this is the metal and bind to the boron and boron. So this is the ligand, which is micro B6H10. Okay, I will proceed the ligand with tetrahepto. So the anionic complex shown in figure 4 can be considered to comprise two bidentate, which is B10H12 2 minus ligand coordinated tetrahedrally to the zinc. As you can see, this is the ligand B10H12 2 minus. Okay, that's all from me. Thank you.
Hi, good morning. My name is Fatma and I will continue the presentation with the structure and name of the metalloborane. So there is a few structure of metalloborane and a variety of deltahedral metalloborane structure were discovered based on the deltahedral topologically distinct from the closed-hole deltahedral. So the first structure of the metalloborane is the closed-hole metalloborane deltahedral. This structure look more likely like a spherical deltahedra and it only have the degree of 4 and 5 vertices. But the deviation of sphericity resulting from the preference of transition metal for degree of 6 and vertices forming this structure which is isoclosal metalloborane deltahedral. And this structure is not like a spherical structure, and the metal atom in this structure are located at the unique degree of 6 vertex, which is here. And the other structure of the metalloborate is a oblato-closal metalloborate deltahedra. This structure is resulting from the boron atom that located at the degree 4 vertices point on deltahedral surfaces of highest local curvature resulting in flattened structure. So that's all from me. Thank you.
Okay, so I will continue the presentation with metalloborane reactivity in hydrogen absorption. So metalloborane are transition metal and borane compounds that transition metal and also borane combine together to form metalloboranes. So transition metal atoms can bind up to 10 hydrogen molecules with an average binding energy of 30 kJ per mole of hydrogen, which lies favorably within the reversible absorption range. So among the first row transition metal, scandium and titanium are found to be the optimum in maximizing the hydrogen storage on metalloborane. So comparing the aluminium, scandium and also titanium, it is known that aluminium have a larger second and third ionization energies than scandium and titanium. Thus, it is more difficult for aluminium to yield its electron to the ring. So as shown, aluminium has the lowest change transfer in both planar and also closed structures, as well as having the lowest boron to boron bond length. Compared to the three transition metals, titanium is the most stable, and it can be partially explained based on the ionization energies of aluminium, scandium and also titanium, and the degree of charge transfer of the metal ions. So titanium is the lowest energy structure and is stable due to the large charge transfer of titanium cation to the boron ring. So comparing aluminium, scandium and also titanium, aluminium is the lowest stable.
Continue with reactivity of metalloboranes. Based on the previous study by Nesbitt, introduce TPB and DPB ligand scaffolds. So these ligands, which are a phosphine ligand that acts as a stigma donor and pi acceptor, while the borons act as stigma acceptor. So, the metal-boron interactions in the TPB can vary from no interactions to a strong interactions. No interactions metal boron that and can develop the eta interaction with the phenylaline linker between between borons and phosphine in order to increase the coordination number and electron count at the metal center. Secondly, for DPB scaffold, Fisher and aryl substituents that act as a stigma donor and pi acceptor. And then arene ligand additional, like arene in edit may display permeability that provide a mechanism for modulating the coordination number and the electron count at the metal center.